Okay, let's have a look at inclined planes. Now we define an inclined plane as a tilted surface where the tilt of that surface has an angle that lies somewhere between horizontal and vertical. Now to analyse motion on this particular surface or this inclined plane, we need to set up a set of reference axes through which we can make our calculations. So the first axis we need to set up is what we call our x-axis, and we define that as the axis along the surface of our inclined plane. We set up a second axis that's perpendicular to this. So this is our object acting through our inclined plane as it sits there. Now we denote that as our y-axis, but we also note that if the object is acting through the plane, then the plane is acting in an equal and opposite direction through the object. So this axis denotes our normal force, or our normal force of the object acting through the plane and the normal force of the plane acting through our object. So we get equal and opposite values. If we calculate one, we know what the other one is. Now we can set up four scenarios here. The first one is where we have an object that falls straight through. So in other words, the angle here is going to be 90 degrees. We find that the net force of our object here is going to be equal to mg, and it's going to act all in the downward direction. In other words, it's going to act along here all vertically. Now if we change the angle slightly from 90, so we shift it back, let's say we put it at 70 degrees, we now find that our force once again is mg acting through this object, but this time we're going to get some component that acts through x and some component that acts through y. To calculate these two values, we need to relate the angle of our plane to our similar triangle here to get our similar angle, and we can then split our acceleration due to gravity through our object through our two axes. First of all, in the x-axis, we're going to get mg sine, because this is opposite of our angle. So we're going to find that our object acting through the x-axis is going to be mg sine theta. Similarly for our y-axis, we're going to get mg cos theta. Now, as a little thought experiment, what happens as we decrease this angle? Well, as we decrease it, we find that the value of x will go down and the value of y will go up. Don't think of this in terms of our normal projectile axes. They're slightly different because our x is actually acting in the downward direction here and our y is acting in this perpendicular direction. Now we can once again calculate our x and y values, and we find that our x will decrease and our y will increase. And we can go to the far extreme now, where we have an object sitting on a horizontal surface. Once again we have our force acting through it is mg, but we see no net movement here. Therefore, what's acting in the x direction will be 0. It'll all be acting in the y direction, but our object will be at rest. So let's look at how we can apply this theory to some common problems. In the first one, we've got a 10 kilo mass sitting on a plane at 30 degrees. And we want to look at the motion of that object as it travels, and we're going to say that this is a smooth plane, so we're going to assume that we have no coefficient of either static friction or kinetic friction. So the first thing we might want to calculate is the net force on this object as it sits on this plane. Now we're looking at what's happening in the x direction, so we need to calculate for our x value. So once again, by similar triangles, we've got 30 degrees here, 30 degrees in this triangle. So x is going to equal x sine theta. X is going to be, if we look at our relationship, we're going to use sine theta as opposite over hypotenuse. Therefore, x is going to be mg sine theta. And if we put in our numbers, 10 kilograms, 9.8 meters per second squared, and sine 30, we find that the net force on this object will act in the downward direction with a value of 49 newtons. If we wanted to calculate the normal force on this object, we would use the relationship that's cos of adjacent over hypotenuse. this one over this one to calculate y. So we get y equals mg cos theta. We've got 10 kilos, 9.8 meters per second squared times cos of 30. So we've got a y value here, or a normal force, of 87 newtons. So we've split our acceleration due to gravity here into its x and y components as it moves down that slope. Now let's say we wanted to know the acceleration on this object. Well, we could go through this process and take out our acceleration due to gravity here and calculate a value, or we could take our net force acting on our object, which is acting through that direction x, to calculate our acceleration. So if we do it this way, we find that we've got a force of 49 newtons, we've got a mass of 10 kilos, which gives us an acceleration down that slope of 4.9 meters per second squared. And obviously we can use this value to calculate a velocity, an initial, a final velocity, or an average velocity, and we can use it to calculate displacement as well. Now we can also do something where we look at an object that's at rest on an inclined plane. So let's take an example. We've got a coin that rests on a 30-degree inclined plane, and we want to know, if it's at rest, what's the coefficient of friction between that plane and our object. And we've put our coin in here as 50 degrees in mass. So once again, we've got our acceleration due to gravity, our force acting through. We're going to split that into our x and y components. Remember that our x component is acting through our inclined plane. Our y component is going to be our normal force. So to calculate, just before we move on, remember that our static friction will be equal and opposite to our acceleration through here created by the slope of the plane. So we know that in this case, acting through this direction, it's our static frictional force that is stopping this object from falling down. We also know that this static friction force is equal to mu, or our coefficient of friction, or our static coefficient of friction, times our normal force. So if we start looking at this, we know that we have no net movement down the slope. So this object moving down is going to be equal to our static friction that's holding it in place. And because these are both in equilibrium, the net force is going to be 0. So those two added together will be 0. We can substitute in here for what we found here. So Fx is going to, or Fx minus mu s times the normal force is equal to 0. We can then substitute in. So Fx travelling in this direction will be mg sine theta minus our coefficient of friction. We substitute in for our normal force here, mg cos theta, all equal to 0. We can start doing some rearranging for our static coefficient of friction, and we find that it's equal to mg sine theta over mg cos theta. We can cross out the mg because they're common, and we get sine theta over cos theta, which is equal to tan theta. So the value of our static coefficient of friction is going to be equal to tan 30 degrees, which gives us a value of 0.58. Something to note, this static coefficient of friction is independent of our initial mass. So we don't actually need to know the mass of the coin. It will be, any object that sits on there will have the same static coefficient of friction, and that's what we'd expect.